Hi, I'm Koduri, CEO and founder of Oxmiq Labs. Welcome to my talk on chiplet quilting for the age of inference. The topic of this conference is AI everywhere. The question on my mind is this vision going to be realized by hundreds of gigawatt data centers, hundred thousands of megawatt edge infra, 100 millions of kilowatt computers, or 100 billions of sub-watt devices, or a combination of all of these things? Now, some of you must be wondering, do we need this amount of energy or this many devices? Where is the demand? Or is it a bubble? I'm not going to talk about the bubble and the dollar economics and some of the crazy valuations and the capital expenditure of various companies. But I'm going to show you that the demand, as we project forward to the next 5 years, is incredibly impressive and should make everybody in the silicon world giddy with excitement. Okay. So let's start with the demand as projected today, right, or as measured today. And this is a statement from Sundar of Google, 1.3 quadrillion tokens per month. Let's put that number, right? Google is at 1.3 times 10 power 15 tokens per month. Okay. Now, I think it's a fair estimate. If we include everybody, it's let's multiply it by a factor of 3. So let's say, Google plus all is, 3 times 1.3. That's 3.9 to the power of 10 power 15 tokens per month, right? Now, the annual CAGR for token demand based on the monthly rates is approximately 3x, and that's actually a conservative side of the demand. And if you use this 3x CAGR for the next 5 years, so so the 2030 number would be this 3.9 times 10 power 15 times 3 power 5, right? And this basically gets you to 10 power 18 tokens per month, approximately. I just kind of rounded up to the nearest. It's like 900 something, 10 power 17 tokens per month. So 10 power 18 tokens per month. Now, how many tokens per second, right? So now let's calculate from here, right? What is the tokens per second? 2030 tokens per second demand would be 10 power 18 divided by, month has 30 days, 24 hours in a day, and each hour has 3,600 seconds, right? So you get to approximately 3.9 times 10 power 11. I calculated it before, so I have it in front of me. You can, pull up your calculators and do the math. Now, the energy per token, how many joules per token? There is a range depending on systems, configurations, various optimizations, batch sizes, and all that stuff. But it's roughly, in the 1 to 10 joules per token range. Let's take, the best number, 1 joule per token. Let's say the energy cost is 1 joules per token. So this, when you multiply that 1 joules per token with 3.9 times 10 power 11, your infrastructure to support 3.9 times 10 power 11 tokens needs to be around, so it is your gigawatts, I call it, right, is approximately 3.9 times 10 power 11, because we're saying gigawatts divided by 10 power 9, right? So that is 390 gigawatts. Okay, so remember this. So this is projecting forward to 2030. This is the power infrastructure we need. And now when you hear the various announcements across the world, by the way, not just North America, Europe, India, there are multiple gigawatt installations just announced in India in the past few weeks. And there are many more announcements, and there'll be 10 or 20 gigawatts of infrastructure being built before the 2030 in India alone. So this number, as you can see, why hundreds of gigawatts are being talked about, and each gigawatt, today's silicon expense is around $35 billion per gigawatt. And when you multiply all these numbers, you get those crazy $1 trillion numbers, and that kind of explains some of the valuations and the crazy market we are in. Now the demand is there. The question is, can we meet the demand? Can we bring the cost of these amazing inference devices down? Can we bring the power down so that these are affordable across the entire world? And doing chiplets with scale, I had the opportunity to have many scars on my back, starting with HBM1, back in 2015, to this amazing 47 chiplets in a single package product called Ponte Vecchio, which powered the US exascale computers. Now the governing equations haven't changed. So I use these kind of basic fundamental equations, which I've shared externally in blog posts. I won't go through each parameter in this equation. I will draw attention to a few key things, right? Again, performance per dollar and performance per watt matter. And there is this notion of generality for the architecture. If it needs to be resilient across workloads, new ways of doing inference, new ways of doing training, you need the architecture to be general enough while maximizing performance per dollar and performance per watt. In the cost equation, there is the packaging element as well, which in the past 5 years or so has become increasingly higher component. So when you do your chiplet designs and architectures, you got to think about cost very, very carefully. So with these governing equations, let's look at the parameters that govern your chiplet choices. The first one is the relative, the dollar per millimeters of different nodes, right? As you can see, post Dennard scaling era, in all the recent nodes, the dollar per millimeter is on steady increase, right? So if you want to use state-of-the-art process node, it'll cost you more. So in your chiplet architectures, you should be very careful in choosing which wafers are going to be in most advanced node and which wafers don't need most advanced node. And if you look at the relative energy per op as well, it is also kind of flattened in the sense that new nodes aren't giving you as impressive reduction in power as during the Dennard scaling era. And again, so you have to trade off, and you still need energy reductions. So how you divide up your high density math op portions into most advanced node and areas of your chip that aren't that math heavy, maybe interconnect maybe analog, maybe SerDes into separate chiplets. So these are the set of trade-offs and choices you have. Now, the third important element is the energy consumed for moving bits. The previous picture was showing energy consumed for operations, math operations, and this is the energy for moving bits. And as you can see, after the recent nodes, they're all hovering between 0.3, 0.4 ratio, so not big improvements there as well. So this is kind of the state of Moore's law, right? Now, on the relatively reasonable modern, state-of-the-art nodes, the key matrix for you to keep in mind, and I now go into physics in femto scale, 10 power minus 15 scale. Math operations are costing anywhere from 1 to 8 femtojoules per bit, 1 for an add and 8 for multiply. And there are several improvement opportunities, whether it's new physics, reduced precision. These are the tricks that we've been playing, and there are some companies doing log math as well. Then moving bits, right, is on die, it's about 100 femtojoules per bit per millimeter. Remember the word millimeter, so the distance matters. And there are several improvement opportunities here as well, like, again, advanced packaging, right, 2D versus 3D. Photonics have the property that they have constant energy, but you pay for the cost of converting from electrons to photons and photons to electrons, and new techniques, new algorithms. And then last but not least, the memory access. So on-chip SRAM access is around 50 femtojoules per bit. And if you go off-chip through the DRAM PHYs and all, you can go 2000 femtojoules per bit. And again, there are many opportunities here as well being pursued by various companies, new materials in memory and near memory computing and all that stuff. So that's physics in femtojoules per bit. And this is a very, very important thing to keep in mind when deciding how you're going to slice and dice your chiplet and how you're going to kind of piece them back together. Now from this, I'll come to the kind of the business end of this talk, because I use the word quilt, right? Chiplet quilting. So what's quilts? I mean, quilts evoke imagery like this for you, right? You see these beautiful patterns, some, beautiful patterns again, and some quilts that are hanging, or, quilts with, more hexagonal patterns. The word quilt for us was inspired by the imagery we saw on the quilts. The quilts I'm going to talk about are different. So before I get into that, I have to get back into some gory numbers again. Okay, so let's look at this data. Okay, so this is the various interconnect technologies. How you connect one chiplet to another chiplet, either on an interposer or on a PCB or on an organic substrate, or you use photonics links and all. They all have different reach, how far they can reach, how much power they consume, and how much bandwidth density they can provide, per millimeter, right? And a good way to look at this, would be a chart like this, okay? And much of this information is publicly available. I think one of the chiplet consortiums publishes this information. But so the trade-offs are, you want very high bandwidth. I mean, ideally, you want very high bandwidth density, very long reach, if possible, at very low picojoules per bit. Of course, the physics doesn't allow you, and this chart shows you have to make, various choices on, whether you're doing, short reach PHYs, long reach PHYs, and also the distance, if they have to go rack to rack, the cabling, all of those are accounted for in your chiplet configs. So now that we got these considerations, right? When we think of chiplets, we generally think of, right, kind of square or rectangular objects, right, like this. So now I'm using some, interesting kind of quilt fabric patterns here to kind of, introduce the notion of chiplets for you. And here, you can think of like, so the blue chiplets having compute, heavy compute, and green chiplets maybe, balance of compute and memory bandwidth. The yellow chiplets may be the memory chiplets or IO chiplets, so combinations of them, right, to make your computer. So that's the idea. While we were building these configs, like, one of my key architects, he's from networking world, he's kind of always annoyed that the crossing the diagonal, right, like a green chiplet communicating to the other green chiplet has to go through the blue chiplets, right? So it's longer latency. And he asked a question to our semiconductor physics expert, hey, why can't we have chiplets that are hexagonal, right? So that I have, 6 neighbors, and all 6 neighbors have equal, latency stuff. And when he drew this picture, that's when I said, hey, that looks like a quilt. And the word quilt, stuck with us. So we have built variety of tools to help you build your own quilts, to optimize for cost, power, performance, and latency, all of these key factors, key KPIs, and to study various architectural alternatives and to help design the right solution. So I want to start off with a known reference point for you all, a Nvidia Blackwell DGX B200 based system. Many of you might know each Blackwell package has 2 chiplets connected with 8 HBM dies, and then all of them are connected through the high performance NVLink and vSwitch network. Okay. Now we built a quilt config of this to study DGX B200. Okay. So now I'm going to go full screen on my code here, and if you look at it, it's a JSON file for the B200 chiplet configuration. You can input various parameters about the chiplet, like the width of the chiplet, height, area, bump pitch, cost to the best of your knowledge, right? Power, the area, some power numbers, and the picojoules per op, picojoules, the total T flops. So and the memory interface. So it's a we can build an entire B200, and we can also specify different workloads to run on it. So these are the chiplets config, and if you go to our workloads, right, you can pick variety of workloads. So if we take this here, it's a DeepSeek model, running with FP4 precision type stuff, right? So I set this up before, and here I go, and I will run a B200 8 GPU analysis, right, for a DeepSeek model. Okay, so when I run this, right, it runs and produces the results file, and if I take a look at the result file, it's inference workload B200. The results are captured here. And what I'll draw attention to here is it shows for a kind of batch size of 1, the throughput tokens per second around 1564, and the energy per token per joules is around 3.5. Okay, so that's to just give you a base reference. Okay, so now we will build a custom quilt. Okay, leveraging some next generation advanced physics that are coming our way. So I start off with a base substrate that could be light based, could be micro LED based, could be one of the light photonics technologies, on which we will assemble a bunch of compute tiles like this. So the green tiles, imagine, are reticle sized dies, and we will stack DRAM right on top, multiple layers of DRAM right on top on this. And just imagine that we built a custom config like this. Okay, now that we have constructed a quilt, let's go to our quilt tool and look at its performance and energy and other parameters. Okay, so here we have a custom compute chiplet with, again, the DRAM stacked on top, same rough die size as one of each of B200 dies. But the key parameters that we change here are, because the DRAM is directly stacked on top of compute wafer, we have 10x the bandwidth, right, for each stack of HBM. So we increased from 1 terabyte per second for each HBM stack to 10 terabyte per second. I mean, I shouldn't be calling this HBM, it is custom DRAM. And the other aspect is we have all the 16 of these chiplets on a huge package or on a huge, light substrate. And the interconnect bandwidth on this is much higher than going through NVLink. Okay, so those are the two attributes that are different than the B200 specification. Now we go here and let's run the custom chiplet analysis. Okay, so I run the custom chiplet analysis and it runs. And now I have in the results folder, if we go here, the custom 16 chiplets JSON, right? And let's look at the batch size one, and let's look at the same parameters we were looking at before. Throughput tokens per second is 22,554, so it's more than 10x faster, right? And because of both the combination of memory bandwidth and also the interconnect bandwidth. And the joules per token, this is the interesting part, is 0.24, right? So we've done dramatic reduction in power from around 3 to 0.2, 10x reduction in power and greater than 10x improvement in performance. Now, mind you, this is a hypothetical, ideal quilt, imagining various interfaces. But the reason I wanted to show this contrast for you is if you plug in the right physics numbers for various interfaces, various dies, your picojoules per bit, picojoules per op, and your cost parameters, you can plan your chiplets for success. So let me wrap up this talk with my takeaways for you. Okay, first, the age of inference is here. The demand is real. And people can argue about how many gigawatts and how many trillions of dollars and all that stuff, but it is incredible opportunity for all of us. Exploit physics to meet the demand. Pay attention to those femtojoules per bit, femtojoules per op, and cost of packaging. The details matter a lot. And chiplets are cool. Chiplets are quite cool tool for you to meet this inference age demand. And we at Oxmiq Labs have built some amazing tools for you. So please call us if you're building chiplets. Thank you.